Okay, so today I'm talking about a network topology, a cost-effective low-diameter network topology that we call SlimFly. So first let me motivate this a little bit here. I mean, we all know that networks are pretty expensive. It's actually the most expensive components. And Dror has given a wonderful talk this early afternoon about how important they are, and so I don't need to say anything about this. But what I want to say is that when you're designing a network topology or a network itself, you have two fundamental limits, and these are pretty clear, right? The first is the router radix, which is essentially the number of ports your switch has, right? So it's trivial to you. And the cable length, which is something that Dror talked about, that Mellanox was actually pushing pretty hard to get to 8 meters, right, with the copper cables. And then, of course, for longer cables, you can use fiber. Then you have two soft limits, which is cost and performance. So this cost and performance is a funny thing because you can really trade off cost for performance. So the question is now, how do you design a very cheap network topology? And I want to start a little bit with an overview of what people have done in the past before I explain what we have done, because we kind of drive these ideas to the extreme. So, well, what have people done in the past? I mean, the best known topology is the torus, and I don't need to really explain it to anybody, but it's pretty interesting that this topology is still used. It's probably the oldest topology because it's really easy to understand. And in Switzerland, we just shut down the last computer using a torus. Oh no! Actually not, it's not the last computer because we still have a blue gene. It's a 5D torus, so we shut down the 3D torus. But it's a pretty nice topology because it's very easy to lay out, easy to understand, easy to arrange in 3D space. Another one that's not as often used is a hypercube. Has interesting features, but I don't want to waste, to spend too much time on the hypercube topology. But SGI was one of the companies that actually pushed this topology quite a bit. Data center people are using fat trees, as you know, leaf switches, spine switches, and top of the rack switch is a very typical thing if you have north to south traffic going mainly from the outside of the data center into my data center. So that is fine, but if you need more bandwidth, as we all know, you would actually build some kind of fat tree-like networks, or if you're a little bit older, you would build class networks or folded class networks, and they're essentially all very similar. They're not completely the same, but they're really similar when it comes to their properties. They support very low radix switches. Of course, your 4 is chosen as a random constant. You can also use 24 or 36, and they have a logarithmic latency and a full bisection bandwidth, right? So I'm assuming that you kind of all know what a bisection bandwidth is. This is if you can route any permutation congestion-free. So this is what Dror talked about earlier today. So these topologies are known since the 50s, essentially. So the Claus network was published in 1953. They're still used today. So it's a very nice topology. Okay, so there was a small interlude with the Kautz topology, right? So as some of you may remember it, the Psycortex system, but that didn't work for too long, so I don't want to talk too much about this. But it's a remarkable topology because it's similar to what we are going to propose in a minute, but it's a directed graph. Okay, so now what happened in around 2005? So the fun thing that actually happened there is that we went from small radix switches to higher radix switches. So this is a general development because we all know Moore's law, right? So chips get smaller and smaller, we can pack more transistors on them. We can easily have larger radix switches, right? So this is what we observe, they grow bigger and bigger and bigger, right? For InfiniBand to 24, 36, and we will soon see much larger switches, as I would assume. So the second thing, we went from copper to reasonably affordable fiber optic, right? So this is also something that just got much cheaper, and you can actually deploy fiber optic in the data center without paying through your nose for it. So what happened based on this? So based on this, people came up with new topologies, so-called low diameter topologies. So this is something that's kind of the new trend in topology design. There are multiple of these. So there's a dragonfly topology, as we've been hearing today multiple times. There's also a flatfly topology, or if you're from HP, you would call this HyperX. And then there's a random topology, a class of random topologies that people have been pushing recently, and our proposal at SlimFly topology. But let me first talk a little bit about dragonfly, because that's really one of the more intuitive low diameter topologies, and it's also very related to what we are operating in Switzerland. It's actually really funny that we're close to the largest dragonfly installation on the planet here at CSCS, the Pitt-Stein machine, right? So this is dragonfly, and the idea is that you have groups of switches. So each of these dots here is a switch. You have groups of switches, and these groups are internally fully connected, or nearly fully connected, like in the case of Pitt-Stein. And then each of these groups is, again, fully connected to all the other groups, right? The details, who's connected with whom, doesn't actually matter too much. Okay, so the quintessence of this topology is it gives you full global bandwidth, and I'll talk about what global bandwidth is at a much lower price. So it's about 25% cheaper than a fat tree for for reasonable network parameters. So the question is now, how cheap can you get while maintaining the same bandwidth? So our answer here is the SlimFly. With this topology, this looks slightly similar to a Dragonfly if you think about it, but it's actually much higher wired within the groups, and this is about a 50% cost of a fat tree. Right? So if you assume the model that I'm going to talk about. Okay, so what does this really mean to design an efficient network topology? And the main intuition, actually this is one of the key points of this talk, the main intuition is if you lower your average distance that your packets travel through the network, you lower your resource needs. And I'm not talking about latency, right? I do not care about latency. I'm saying I lower my resource needs because the longer a packet travels through my network topology, the more cable it occupies. And the more cable I need to buy in order to route for this network, right? So this is really the intuition. And so now we view this average distance as the primary optimization target, right? So the nice thing is we can actually now talk about what the optimal topology would be in that case. So the optimal topology is really a graph, so we model a topology as an undirected graph, right? Because this is how we connect the nodes. And for an undirected graph, there's a graph theoretical measure that's called the Moore bound, which really gives me the number, an upper bound to the number of routers in a graph with a given diameter and the network radix. So diameter is the longest path between any two nodes in the network, right? And the radix is just the number of ports I have in my switch. So it's a highly practical thing. So how do I construct the Moore bound? Let's do a little bit of math here to wake you up. It's a rather simple thing. So we start with a single switch in the middle, right? So the Moore bound is 1. Plus, well, how many switches can I connect to this single switch? Well, k. Right? That's pretty clear so far. How many switches can I now connect to these other switches that I just connected? Well, it's k minus 1. Right? Because 1 is taken by this switch, and then I can attach more. Okay, great, and I can continue this, and I will get this square here, so essentially it's growing exponentially with the diameter, and the equation at the end is this, right? It's a rather simple exercise. So now the question is, oh, this is our upper bound. We cannot be better than this, right? We cannot fit more switches into a into a network of limited diameter. So the question is, how close can we get to this guy? Or how close are other topologies to this guy? The answer is pretty far away, and we'll discuss this a little bit more later. So the idea here is that we designed a topology that has a fixed diameter 2. So this is shorter than any diameter that in any topology that you know, essentially. It's just 1 higher than a fully connected graph, right? Okay, so how do we design a diameter 2 topology that's close to the optimum? And this is slightly more complicated because we're using techniques from graph covering, and I don't want to go into too many details because that will probably be really boring. But let me give you the intuition, and I will also explain you how to construct it, right? So the intuition is that we have 2 subgraphs of this topology. Each of these 2 subgraphs has identical groups of routers, right? So this guy has 5. So 2 subgraphs, subgraph A, subgraph B. This guy has 5 groups, 1, 2, 3, 4, 5. Each of these groups has 5 elements, and they have identical structure, okay? And then there is subgraph B that has the same thing, has 5 identically structured groups. I will talk about how these groups look in detail in a couple of minutes. And of course, this is not a good topology because it's not connected, right? So these guys are not connected. So of course, there are global connections from each group to each other group. So it forms a fully connected bipartite graph. So again, if you know Dragonfly well, you will think like, that's very similar. It is. We'll talk about the differences in a couple of minutes. So how do we now create this topology? So now I have to talk a little bit about math and finite fields and things, but you really try to follow the intuition. Even if you're not the biggest math person, follow the intuition. It's not that hard. So first we have to select a prime power, right? And this is where most people say, oh my God, what's a prime power? It's any prime number to any power, right? So 2 is a prime power, 4 is a prime power, 8 is a prime power, 16. So all these nice numbers that computer scientists really like are prime powers, right? So we can take any of these numbers and decompose it into this, but this doesn't matter too much. So once we chose a prime power Q, we will have a number of routers that's 2Q square. So essentially here, Q by Q and Q by Q. These are the 2 subgraphs that we have. The network radix is just 3Q minus delta divided by 2, but that's not that important. So then, after we've chosen a prime power, let's just assume for simplicity that we chose a prime and not a prime power. So just any prime number like 11 or 13. So here, we have to construct a finite field to this prime power, and this is, again, this sounds a little bit interesting. If you know Galois field theory, it's rather simple and pretty much the same. We just construct a finite field that goes from 0 to q minus 1. It's a set of numbers from 0 to q minus 1, okay? It's not that hard. Okay, so of course all in modular arithmetic modulo q. So for our example here, if we choose q equals 5, which is a prime number, right, 5, we get a 5 by 5 network topology, and again 5 by 5, so it's 2 times q squared. The network radix is 7 if you plug this guy in here, and your finite field is 0 to 4. Okay, great. So now the question is, how do we connect these graphs? So now we have these two graphs, as I mentioned at the beginning. So we have to connect them somehow. We have to put wires in this network. Okay, so first we have to give them names. And the names are extremely simple. So the names is, well, we have two elements in the first naming scheme. So we have 3 sets in a 3-dimensional space in how we name them, right? So the first one is 0 or 1 that identifies the graph. And then we have essentially our finite field q times the finite field q, right? So they live in 0, 0, 0, 0, 0, I mean 0, 0, 0, 0, 0, 1, 0, 0, 2, and so on. So it's a pretty simple Cartesian space that we arrange these guys on. Okay, good. So how do we now connect these guys? And this is, again, a very simple rule. It may sound a little bit funny with all these signs, but it's a very, very simple rule. So the simple rule is we have to find an element, eta, that generates a finite field. And this is, again, something very, very fundamental that many of you probably learned in grade school. So what does this mean if you generate a finite field? It really means that you have to take this element eta to some number, and to any number I, any real number, and it has to generate all the elements in the finite field. So this is rather hard to find, but you can actually compute it really easily if you have enough compute power. So for this finite field 0 to 4, eta equals 2. Right, and you can check it. You will get to any of these numbers in modular arithmetic, but the 0, of course. But the 0 is an exception. Okay, so now we find this eta, and then we build 2 sets. One of the even powers of eta and the odd powers of eta. Right? Okay, so it's still just a very simple way to arrange these things. And then how do we connect now these graphs? So now we have our 2 sets, even powers, odd powers. And we connect them, very, very simple again. We take subgraph 0, this guy, and each group in this graph, right? Remember, these groups will have identical structure. And we look at the first element in this even powers of the subgraph, right? This is 1 in this case, because 2 to the 0, I mean, the eta was 2. 2 to the 0 is obviously 1, right? And so we connect all of the graphs that have Manhattan, all of the vertices that have Manhattan distance exactly 1 in this graph. Right? Then we look at the second element. This is 4, and we connect all of the vertices that have exactly distance 4. Right? So then we do this for all of these groups. And we do this for the right group, because here it's 2 and 3, right? And you could have plugged this all in, and we get this graph. Okay, great. So now the question is, well, there's still some connections missing. These are the global connections between these two things, right? So here it's a little bit more involved, but it's also relatively simple if you don't care where it comes from. So it's essentially y equals mx plus c. If this equation is true, we connect the graphs. We connect the vertices, right? And again, this is all in our naming scheme here. So we call them 0xy and 1mc. And so we can create one example here and another example here. And once we connect all of them, the magic is that we will actually get, in this particular example for q equals 5, that we will get a graph that is well known as the Hofmann-Singleton graph. This is actually one of the only graphs that attains the Moore bound, so that is strictly optimal with respect to the Moore bound. There are exactly 3 of these graphs. One is the Peterson graph, which probably many of you know, the Hofmann-Singleton graph, and there's another graph which is not known yet that has this property. Okay, good. So another question is now, well, we now build a topology. So we have a full construction rule for a topology, which I'm claiming is close to optimal in terms of cost, right? So the question is now, how many endpoints, how many computers are we going to attach to every single router? Because it's a direct topology that we are building. Okay, so here again, these are the vertices, or these are the edges that go towards the topology, connected in the way that I just described. And these are the vertices that go towards endpoints, right? Every switch has a set of end nodes. So now the intuition, your intuition is probably right. What do? It's a diameter 2 network, which means that 1/3 of the end of the radix goes to endpoints and 2/3 go up. Why is that the intuition? Well, what we want to do is we want to send, I mean, the traffic pattern that we really care about is random uniform traffic, right? So this is, I just take this as an assumption. We want to send to all the other nodes as fast as we can. And what this topology guarantees is that there is enough bandwidth that I can send to all other processes at full injection bandwidth, right? So each of these computers can send at full injection bandwidth to all other processes, assuming an ideal routing. Right? We'll talk about routing in a couple of minutes because that's not that ideal in practice, right? Okay, so, and this is why we attach 1/3 here and 2/3 here, because if this 1/3 will generate a stream of 1/3 out here, so we'll occupy 50% of the outgoing links, right? But since it's a diameter 2 topology, from other hops, there's incoming traffic which leaves again, right? Because I have to hop through another switch. This is the other third that I'm hopping through, right? Actually, for Dragonfly, this is rather intuitive. A Dragonfly is a diameter 3 topology. Here, 25% go down and 75% go up, for exactly the same reason that I just explained. There's also a more mathematical argument, but I think this is intuitive. Okay, so the question is now, how close are we to this optimality, to this bound that we just established? Here is the bound, right? So we are always 88% close. So this is a construction that's well known in computer science. And then there are other networks that are much further away, right? If we build them in a diameter 2 construction. Okay, so now you should believe me that there is a way to build this topology at this point. Even though you may not have fully understood it, but there are papers that you can read about this. But it's really about the concept, right? So there's a way to build this topology. And now the question is, well, is it actually cheaper than other topologies, and Dragonfly, and Fat Tree, and whatnot? Okay, so let me explain. So this is how it looks like for this particular example. So what we first do, because there are lots of global cables, we first do is we mix these groups, because this arrangement is rather bad, because if you just mix them, meaning group 1, group 0, or group 0, 1, 0, 1, 0, 1, right? We can shorten the global cables, right? The second step that we can do is we can actually merge these groups pairwise into one group, right? Because then we can form racks with these guys, right? So we can just put them into a single rack. And then we have less global cables, so less long cables, right? So this is the goal, to minimize the number of global cables. And these racks form a fully connected graph. And now again, you may say, well, this thing again reminds me a little bit of a Dragonfly, because again forms a fully connected graph at the end. And now let me discuss the differences to a Dragonfly. And they're highly unintuitive. But this is why it's so cool. So first of all, what we have is many intergroup cables, essentially 2q minus 1, right, for the prime power q that we picked at the beginning. So many intergroup cables. So for Dragonfly, we have exactly one intergroup cable, right? So every Dragonfly group is connected to all other Dragonfly groups with only one cable, right? Here, there are many cables. So the other thing that we have is we have 50% fewer intra-group cables, which is confusing, because why would you do this, right? Why would you have in the local group less cables than externally? But this is exactly what you need in order to get the other benefit of this topology. The other benefit is that you have 25% less routers than a Dragonfly. So you need to buy less switches, right? That's where the cost savings comes from. And you have a 33% higher endpoint density, right, if you do the math. Meaning that overall the topology is about 25% cheaper, because you can just use less switches to connect the same number of endpoints. Okay, so let me now discuss a little bit of a cost model. So we've analyzed the cost in detail, because now you could come and say, well, you know, but fiber cables are more expensive than copper cheaper than copper cables. No, more expensive than copper cables, and all these things, and I want to lay it out. So we use the standard model to evaluate the cost of this topology, which is essentially a data center. We arrange it as square as possible. It's just a model that many people use. It's, by the way, the same model that was used for Dragonfly topologies, right, in the ISCA paper. And so we assumed that their numbers, we wanted to have an apples-to-apples comparison. And each of these boxes here is essentially a rack, and there are top of the rack switches, and they're 1 meter by 1 meter, but that's really a model that is not really useful for you. It's just useful for comparison between different topologies, because you would need to do this on a case-by-case basis for every data center, right? So you can't use this model. But it's a fair model. What we did then is we just designed our own cable cost model. So we checked Colfax Direct, which was also mentioned a couple of times today, just for the cable pricing. So just to figure out how expensive are these cables, and we used various Mellanox cables for various technologies. And here's just one of the diagrams. We have many more for different technologies. But here you can see that the optical cables, they start at a pretty high cost, because of course you have to buy a laser. But the material, the fiber itself is not that expensive, so they can go very long distance. Well, the copper cables are very, very cheap, but there's an upper limit to the length of these cables, right? And this morning, we heard that they're now slightly longer than in this graph, but still, it's not too long. It doesn't exceed 10 meters. Okay, so then we have a similar model for the router cost. So we just again went to Colfax Direct and checked the router costs for, again, Mellanox equipment. And I think this is for FDR, but we again see in one of these nice functions, and these are the cost functions that we use to evaluate these topologies, right? So if you now look at the final result, and I can go more into detail how we exactly did this, you can see the cost for these topologies is significantly different, of course. I just want to mention some, so there's a fat tree here, and then significantly cheaper is the Dragonfly at the same performance, right? So we are comparing a fully non-blocking fat tree with a fully bandwidth Dragonfly with a full bandwidth Slimfly, which is again 25% cheaper than the full bandwidth Dragonfly. So Slimfly is about half the cost of the fat tree, and I can give you a little bit more intuition why that is the case, right? So in the fat tree, there's a lot of wasted bandwidth because you go up and down. In the Slimfly, you go right to the destination, right? That's one of the intuitions. And in the Dragonfly, you just have 3 hops instead of 2. So that's where the 25% switches come back. Okay, good. So now, one of the interesting metrics you may also look at is how many cables do you have to cut randomly before the network gets disconnected? That's more of an academic metric because nobody will wait that long for your data center to degrade. But it's a very interesting metric because you can see that, for example, a torus, I mean, this is number of nodes here, and here's how many percentage of the cables you have to cut on average before the network becomes disconnected. Right? Torus is easy to disconnect here, 10% at 8,000 nodes. But other topologies like the Dragonfly are rather hard to disconnect. And actually the random topology is somewhat the hardest to disconnect because of course the cable is there randomly anyway, right? So if you remove one, it may not be that big of a problem. And the interesting fact is, what really surprised us is that Slimfly is as resilient as a random topology. So I can now explain why, but that'll take a little bit of a longer discussion. But ask me offline if you're really interested. So now let's do a case study. So let's assume we want to build a data center with about 10,000 nodes, right? Okay? So this requires a switch with a degree 43, which already tells us, well, we can't buy this switch today, but maybe tomorrow. So this kind of means you're limited in the maximum network size by your switch degree, right? So with today's technology, you can easily build 5,000 nodes without problems at a cheap cost, and we need 722 routers. So let's compare this to other topologies. So here are different topologies. Let's look at topologies that use the same switch technology, right? So if you look at the cost per node, there are more metrics here that you can look on offline, but if you look at the cost per node, we again see that we are substantially cheaper than fat tree and all other topologies essentially. But now you may say, well, I don't care about the switch technology because that gives me different endpoint numbers. Let's just look at comparable endpoint numbers. And again, each of these topologies are the optimal construction for them. This is why they're not exactly 10,000 nodes besides the flattened butterfly, right? Whatever you can build reasonably or optimally in that case. And again, we're significantly cheaper, so at least 30% cheaper than the next cheapest topology, which is Dragonfly. Okay, so by now I should have convinced you that we can build it. It's cheaper, and now the last question remains, well, does it actually perform, right? Does it actually give me a bandwidth after all? So in order to talk about the bandwidth or about performance numbers for topology, I need to talk about routing. Okay, so routing is a little bit of a hairy issue because there are many, many different routing metrics, and usually the hardware only supports a very small subset of them. But let's just assume we have good hardware, okay? For these low diameter topologies, we definitely need adaptive routing. Or some form of random routing. Okay, so we use the following routing protocols. So first is minimum static routing, which is very easy with today's InfiniBand, right? So it's just minimum static routing, very simple. So where we essentially route an animation, you write from the source to the destination, okay? The second one is using valiant routing, which is, again, a nice routing algorithm because it disperses traffic throughout the network. What that means is you pick a random node, a random other node, route along the minimal path to that random node, and that random node routes along the minimal path to the actual destination. Right? So a super simple routing algorithm. The next one is then adaptive routing, like we heard again from Dror. So this comes in 2 versions, like he nicely explained, so I don't need to explain that much. It comes in one local version, where we essentially look at the local output queue length of each switch, and the switch kind of makes a local decision. It doesn't know what's going on in the remaining network. And it comes in a global version, where we assume we know all the queue lengths of all the network, which is of course hard in practice because it has all kinds of issues, as we heard this morning. Okay, great. So what we simulate here is uniform random traffic in this case. So uniform random traffic, how does it work? Well, everybody sends uniformly random to everybody else. So this is a relatively simple pattern. This is, by the way, the pattern that is underlying the Graph 500 benchmarks and many big data computations, because it's probabilistically distributed traffic through the network. So it's also one of the harder traffics you can put on a network, because everybody injects at full speed, right? So it's a very demanding traffic pattern. So here's the result, and this is a little bit hard to read if you're not used to these diagrams. The idea here is that we have the latency in cycles, so small is good, right? Or small is better, and the load at which every node injects into the network, right? So it starts from close to zero load, which we can immediately see that, of course, SlimFly with minimum routing is best because it only has 2 hops. Right, so you can't beat 2 hops, right? It's just better latency. And then let's just compare to fat tree is up here, because the fat tree has 4 hops, right? You have to go 2 up, 2 down, right? Okay, so, but nobody really cares about latency, so it's not waste too much. And Dragonfly is in between, by the way. But let's talk about bandwidth. And bandwidth is essentially, the maximum bandwidth of such a network is the position where this goes to infinity, right? Essentially, the intuition here is a node cannot push more traffic into the network, it will be backed up, right? Because here, this is how much traffic you push in. Ideally, all of these topologies, all of them, should support 1.0. They should support 100% injection, if the routing was perfect. Of course, the routing is not perfect, because various effects, head-of-line blocking and all of these things, right? So this is a cycle-accurate simulation, and thus we don't get that much performance. What we can see is that fat tree is actually the best one, exactly like we would expect, because it has twice as many resources, because fat tree performs extremely well if you route it right. Right? The other topologies are harder to route. So for example, Dragonfly gets lower bandwidth because the routing has more opportunity to screw up. Because it doesn't have any, the intuition here is that it doesn't have any excess cables. Right? If you make a wrong decision, you're going to hinder somebody else in his traffic. In a fat tree, you can make a wrong decision. It's not that bad because you have excess cables. Right? In the SlimFly, and this was also surprising to us, we actually perform better than the Dragonfly. We were expecting to perform about as good as the Dragonfly. And the reason why this is that the routing mechanism, again, we have these imperfect routing mechanisms, right? This is UGEL, G or L, and you can find the details down here. So the routing mechanism is not perfect, but in the SlimFly, we only have 2 hops to the destination. So that's 1 hop less than the Dragonfly, where the routing can screw us over. Right? So if the imperfect routing is there, right? If I route less to the destination, I of course have less chance of making routing mistakes, right? Okay, good. So we have lots of other results for different traffic patterns and different other things. We have a paper at SC and for different buffer sizes if you're a switch vendor, and for different cost and power results, different case studies, bisection bandwidth, a theoretical measure, average distance also as a theoretical measure. So there's lots more data on this topology if you care. And so to just summarize briefly, we designed a new topology, right? And the new idea is to optimize towards the Moore bound. So you're using a mathematical optimization framework to actually achieve what we believe is the optimal topology. We found advantages in essentially all metrics. Let me repeat this, all metrics that you can measure a topology by. We're at least as good as the best contender, right? We used the mathematical optimization approach, as I just mentioned. My student did most of the work, of course. And just the quick summary, so the takeaway message, if you didn't listen at all, so wake up now and at least get the takeaway message. So we have a lowest diameter topology. And this is the funny thing, is the set of configurations is actually higher than the set of configurations of full bandwidth Dragonflies. Right? So we can build more SlimFlies for a range of sizes with a given switch degree than we can build Dragonflies. So it's more resilient than a Dragonfly as well, right? So we are 25% less expensive than a Dragonfly and 26% less power hungry. So the intuition is again, well, we have 25% less routers, right? If you don't need to buy 25% stuff, you're of course 25% cheaper and you also use less power, right? So it's kind of clear. And then we have lowest latency, of course, because it's diameter 2 only, right? And they have a full global bandwidth, which we just showed, of course, modulo the routing technology. And if you don't want to construct these topologies yourself, we have a large set of graphs on our webpage. You can essentially say, look, I want to build a certain network with a certain degree, and you can just find the right graph on our webpage, right? And then build it for yourself. Thank you very much, and I'm open for questions.